guess without further ado, we can start. So, actually, wait. Did you start recording YTG? Okay. So, for this week, our topic is going to be essentially comes down to a couple of very important theorems, and the idea is just around the convex hulls, which we have encountered in a couple exercises in chapter 1. And so we want to know, okay, what can we say about them? We saw that in cases of, let me see here. So we want to know what can we say about convex hulls and how can we, make them useful. If you recall, the convex hulls are the intersection of the convex sets that contain a certain set. So this is the convex hull. I did define it in the next slide. And we're going to see under certain constraints, okay, what happened to the convex hull of a set? If the set is compact, can we say that the convex hull is compact? If it's closed, can we say it's closed? We know that in case of open sets, it is open. And even changes in the space itself, okay, if axis stars separate points, what can we say further? If it's locally convex, what can we say? And the most important theorem, I think, is the Krein-Milman theorem, which is related not only to the convex hull, but to extreme points. And so the first important of the Krein-Milman theorem, which we're going to see, is that in certain situations, if you want to prove certain things exist, so take it as the similar to the Banach and Spirit. If you want to prove something exists, the Krein-Milman can serve that purpose because you may have noticed that it shows extreme points exist. So in certain situations, if the thing you want to prove exists is the extreme point of a certain set, then the Krein-Milman theorem tells you it essentially exists. So, and it actually tells you that the set of extreme points is quite large. So it works in a way that guarantees the existence of certain things. A second concept we are going to study is extending certain concept to values that lie in a topological vector space, which is first of all integration. And there's another concept of integration that is defined somewhere else. I forgot the name of the integral for vector values, but for our purpose right now, I think this should be sufficient. And we're going to define it in a very interesting way, just based on what properties we want our integral to satisfy. And moving from this, now that we have, after we finish this section, now that we have a form of integral on functions that lie in topological vector space, we can extend concept like a holomorphic function. We can even extend like a variety of topics, but that's another story. So first of all, in chapter 1, we have solved the convex hull. Recall that it's the intersection of all convex set that contains A. We proved in exercise, I believe it's 2 or 3. We proved that it's exercise 3. We proved that the convex hull of open set is open, and if X is locally convex, then we showed that the convex hull of bounded sets is bounded. So now we, as I was mentioning, we want to know what can we say about the convex hull of compact sets, because even in Hilbert spaces, which are, relatively well-behaved spaces, the edge need not be closed, and there are cases which the closure is not even compact. So, and can we even relate like the convex hull to the set itself? This is like the purpose of the Krein-Milman theorem. Well, it relates extreme points, but the convex hull of the extreme point to the set itself. So, first of all, some definitions. The closed convex hull of E is the closure of the convex hull, just denoted by cobar. And this is important because, as you saw here, we can't say anything about the convex hull being closed. So often the results will be about the closed convex hull, as you will notice. But there are certain spaces where this is not a problem. We just want to prove it more generally. And recall that in a metric space, we have something called totally bounded if it lies in a union of finitely many open balls of radius epsilon, where every epsilon positive. And a set E, so this concept is in a metric space, and just like in chapter 1, where we extended boundedness to, boundedness in a topological vector space, and it turns out that they are different, like the metric boundedness and the boundedness. We can also generate a basically topological vector space equivalent of total boundedness. And this is just to serve us in a certain proof that is to come. So we said it's totally bounded if for every neighborhood of 0, we can find a finite set F such that E is subset N F plus V. And once again, if X is metrizable, then these concepts are the same, but if we restrict ourselves to invariant metrics that are compatible with the topology of X. So this is essentially the same as the concept of boundedness, where we try to generalize it. This is just for total boundedness. So, yeah, again, in free spaces, for example, which are going to be, most spaces you'll encounter in practice, the convex hull do act nicely. For example, if the sets A1 to AN are compact, then in a compact convex sets in a topological vector space, then the convex hull of the union is going to be compact. If the space is locally convex and E is totally bounded, then the convex hull is also totally bounded. This is in line with what we proved in chapter 1, that if it's bounded, it was an exercise, then the convex hull was going to be bounded in a locally convex topological vector space. I think there was an example where outside the locally convex spaces, it doesn't work. So if X is a free space and K is compact, then the convex hull is going to be compact. So this is essentially very useful because compactness is useful in general. And if K is a compact set in Rn, then the convex hull of K is going to be compact. I won't prove all of them just for the sake of time. I've left only the proofs that I thought are major, so we're going to be proving the last 2 points. So we are trying to prove that if K is compact, then the closure of the convex hull is going to be compact. And we're going to prove this by using the things we proved here. First of all, if X is locally convex space and E is totally bounded, then the convex is totally bounded. And we are going to use total boundedness to conclude that this set is going to be compact. So first of all, the closure of totally bounded sets are going to be totally bounded metric spaces, and hence are going to be compact in complete metric spaces. So if K is compact, then K is going to be totally bounded, right? And by part 2, the convex is totally bounded, and so we conclude that it is compact because we are working with Fréchet spaces. Remember, Fréchet spaces are complete with the invariant metric. As for the second part, we want to prove that if K is compact in Rn specifically, then the convex hull is going to be compact. We don't need the closure anymore. So it's actually quite a nice proof. If we let S to be the simplex in Rn that consists of the T's, the vector T's, where the sum of the Ti's are going to be 1, and this shouldn't be a surprise why we need this, because remember, another definition of the convex hull is that it is the finite convex combinations of members in it. So every member, you can write it as a linear combinations where the sum of the scalar is going to be 1. So that's why we started with this. Now we're going to admit this. There is a proof for it in the book, which I didn't think it was that insightful to include it. If E is a subset in Rn and X is in the convex hull of E, then X is going to be in the convex hull of some subset of E which contains at most n plus 1 points, which tells us that X is in the convex hull if and only if X can be written in this form. There's a plus here. That is not, this is not plus dot plus. Sorry. So anyway, for some T in S and Xi in K, which means in other words that the convex hull is going to be inverse the image of S cross Kn plus 1 by the continuous mapping that takes T, the vector, and x1 to xn, and gives you this. And this is obviously going to be continuous because it's just addition and multiplication, which are continuous operations in a topological vector space. So we get that the convex hull is compact. So we just proved that in the Fréchet space, we have these nice properties. This is not in general true. We have that the convex hull of compact sets is going, the closure of the convex hull in compact sets is going to be compact. And in Rn, the convex hull is going to be compact. So yeah, so now we're going to build towards the Krein-Milman theorem. So first of all, we're going to prove a certain analog of the geometric Rahan-Banach. The geometric Rahan-Banach is theorem 3.4 in Rudin. It's called, I think, separation theorem, which is the theorem that requires local convexity. That's how I remember it, at least. which will be used in the proof of the Krein-Milman theorem. So suppose X is a topological vector space on which X star separate points. This is almost always crucial, which if you've seen like the proof, the fact that X star separate points is key in most of these things that we have been working with. So, which is true in locally convex spaces, of course. I think we proved. I'm not sure if Rudin proved it. I think he proved that in locally convex spaces, X star separate points. So
yeah, that was definitely proved.
Nice. So suppose A and B are disjoint, non-empty, compact, and convex sets in X. Then we can find a functional in the dual such that the supremum of real lambda of X for X in A is going to be strictly less than the infimum of real lambda in Y for Y in B. So notice that the hypothesis here is weaker than that of geometric Banach because local convexity, or I write here, local convexity itself implies that X are separate points. So now to make up for this, we assume both A and B are compact, which is more than the geometric Banach here. Now, for the proof of this, we let XW be X with its weak topology, and A and B are compact in XW. Because they are going to be in a Hausdorff space, they are going to be closed. And because XW is locally convex, the geometric Banach theorem can be applied to XW in place of X. So this gives us a linear functional in the dual of X star that satisfies this inequality via the geometric Banach. So we've moved from a normal space to a locally convex one, use the geometric Banach, and now because X, the dual of the X with the weak topology is itself the dual, then we get our result. And the fact that this is true is a consequence of the following theorem, which if X is a vector space and X prime is a separating vector space of linear functionals on X, then the X prime topology makes X into a locally convex space whose dual space is X. You can apply this for linear functionals to get the result. Okay, so now we are ready to tackle the Krein-Milman theorem. But first of all, we define the concept of extreme points. So if K is a subset of a vector space, a non-empty set S is called an extreme set of X if no point on S is an internal point of any line interval whose endpoints are in K, except when both endpoints are in S. So the points are never an internal point of a line interval unless the line interval itself lies in S. In a way, they are the extremity of the set. There's the photo that I've had at the very start. This shows the extreme points essentially. So these points right here, this whole thing would be the convex hull, by the way, which is a intersection of the convex set. So extreme points would be on the extremities of the set. Now, where were we? Here. So, and the set of the extreme set that are consistent of singletons are going to call the extreme points and will be noted by EK. So, and this is the Krein-Milman theorem, which tells us that if X is a topological vector space on which X are separate points, so this is true for locally convex spaces, of course, and if K is a non-empty compact convex set in X, then K is the closed convex hull of the set of extreme points, meaning that K is the closed convex hull of a set of extreme points, which means that the set of extreme points is actually quite large, as Rudin says. So, and we're going to prove this theorem. And there are certain details that I didn't include. I just included like the general ideas, or the general picture at least. So we want to show that the set of extreme points is not empty. And the argument, because this is an existence theorem, like the Banach, I think it's natural to expect that the argument is going to be in the shape of, okay, we want to build certain sets and try to use something like Hausdorff maximality or Zorn's lemma or so on, right? Because it sort of tells you, like, if you want to prove something exists, at some point, you have to go back to either the axiom of choice or its equivalences, at least, which it's not, by the way. A fun fact that's unrelated to this, the Krein-Milman theorem is weaker than the axiom of choice, I'm pretty sure. There's an interesting, like, order theoretic fact about it, where, like, the Krein-Milman theorem with the Banach theorem imply the axiom of choice. But that's another story, of course. So, let P be the collection of all compact extreme set of K. Because K itself is an extreme compact set of K, then this set is non-empty. And we'll admit the following two properties. These are proven with Rudin, but I didn't want to, write the whole proof down. So the intersection, first of all, the intersection of n and non-empty collection of P is going to stay a member of P unless the set is the empty set. And if S belongs to P, lambda is a linear function, and M is the maximum of real lambda of X on S, then this set, S of lambda, which are the set of points such that real lambda of X is equal to the maximum value, is a member of P. And this is going to be key to our proof. So, first of all, what we're trying to prove right now is that an extreme point exists. And we're going to prove that the minimum in this set, or the least element that does exist, we know that it exists, is going to be an extreme point. So first we choose some S in P. And we know by P prime the collection of all members of P that are subsets of S. So because S itself is a subset of itself, it's going to be part of P prime. So P prime is not empty. Now we partially order P prime by set inclusion and let delta be the maximum totally ordered subcollection of P prime. And this exists by, this is where, choice comes in, or a form of choice comes in. Now we let M be the intersection of all members of omega. And because omega is a collection of compact sets with the finite intersection property, the intersection is not going to be empty. So, first of all, we know that the intersection of any intersection of subcollection of P is going to be a member of P. So M is a member of P. And now we're going to prove that M is actually going to be our extreme point. First of all, the maximality of lambda of omega, implies that no proper subset of M belongs to P. Now it follows from 2 that every lambda is going to be constant on M. And I think Bango pointed out why only the real part being constant is enough, because you can apply it to the complex part as well. And the same argument follows. So now because X star separates points on X, M has only 1 point, because if it had 2 points, then we can find a lambda that takes a value on 1 point different from the other point. So we wouldn't get this result. So again, the separation of points is what saves the proof here. This means that M has only 1 point, and therefore M is an extreme point of K. And this strategy of using the fact that X star separates points has been, I've seen it to be quite common in most proofs. Keep your eye out for it. So now that we have an extreme point of K, which does exist, although by the axiom of choice, but it does exist. Now I want to prove our actual claim that K is equal to co-bar of E of K. So first of all, we have proved that every compact extreme set of K contains an extreme point of K, right? Here, because we then can do the same process for any point S, and we'll find a subset of S, M, where it's going to be an extreme point that belongs to S. So all of these sets contain extreme points. Now, because K is compact and convex, we get this inequality. Because remember, convexity tells us that K is a convex set that contains EK. So co of EK is subset of K, and because it's compact and closed in this case, then the closure is going to be a subset of K, because the closure is the smallest closed set that contains it. And this shows us that co of EK is compact because it is closed in this case. I don't know if this mentioned. Yeah, because it's the closure. Of course, it's closed. Sorry. Yeah, so the closure is going to be compact. And now assume for contradiction that there's some X in K that is not in co-bar of K, and we're going to reach a contradiction. First of all, the different version of the geometric harmonic we proved here is going to give us a lambda that takes this value, or where this value is going to be less than this value. This is going to be the key to our proof. We'll use this set. So we get a lambda in X star such that real lambda of X is that and real lambda of X for every X in the closed convex hull of the set of extreme points. Now, because k lambda belongs to P, our choice of lambda shows that k lambda is going to be disjoint from this set. Because if these points were to belong to this set, then they would take the maximum value real lambda of x would take on S, which is impossible because we know that they're less than lambda of x0, and x0 itself is in k. So we know that they can't take this value. They're going to be less than. So k lambda is disjoint from this set, and this contradicts that the set of extreme points intersection S is not equal to phi for all S. And this is our contradiction here. So we have shown that K is now the closed convex hull of its set of extreme points, in this case at least. And notice that the convexity of K was just used to show that co-bar of EK is compact, right? So if X was to be just locally convex, the compactness here would not be needed. And we can use the geometrical Banach itself in the proof instead of this, and we obtain the following version, which is that if K is a compact subset of a locally convex space, and most spaces we'll work with will be locally convex, then K is going to be subset of its the closed convex hull of its extreme points, which means that the closed convex hull of K itself is going to be equal to the closed convex hull of the set of extreme points. In this situation, this means that the closed convex hull of K may have extreme points that are not in K. This was exercise 33, I believe, which is the last one. Now, luckily, this thing, it doesn't happen if Fouché spaces, which again, like are most of the practical spaces you'll encounter. So it's nice to know that these sort of things you don't have to worry about. So if cobar of K is compact, it does not occur in Fouché spaces. Yeah. If K is a compact set in locally compact space, and if cobar of K is also compact, then every extreme point of cobar of K lies in K. So we avoided this pathology here, where this has extreme points that are not in K. So this will be, there is a proof of the Milman theorem, but after going over it, I've decided not to do it because there is some rather technical details that I couldn't feel bothered going over them, and I'm sure it wouldn't be very useful right now. So now we'll move to our second topic, which is vector value integration. By vector value, I mean the values are going to start lying in a topological vector space. So this shows like one way to do this, by the way. If you go online, you'll find a lot of methods to do this. This was just like the method that Rudin took. So don't take this as the only way we can integrate vector value functions. There are many variable ways. This just works well with what we want to work with right now, which is, in functional analysis, this is the definition that you would want to at least have. So we want to define integration of functions that go from a measure space Q, this is Q by the way, it looks weird in Beamer for some reason, and whose values lie in the topological vector space. That is, we want to define the integral of f d mu, which we want to satisfy that for every lambda in x star, we have lambda of integral of f equal to integral of lambda of f. And this holds for sums, right? And the integral, because we wanted to represent the limit of sums, like in the usual, Riemann way at least, and even like Lebesgue measure in a certain way. So we want to, and this small fact is going to be the key for how we define the integral. We just want the function to satisfy this, basically. So first of all, suppose mu is a measure on a measure space X. X is a topological vector space on which X star separate points, and F is a function from the measure space. These are supposed to be the same notation, by the way, into X, such as the scalar function lambda of F that takes Q to lambda F of Q. These are going to, remember, F of Q is going to be a vector value now, so this makes sense. They are going to be integrable with respect to mu for every lambda in X star. If there exists a vector y in X that satisfies lambda of y equal to integral lambda of f for every lambda in X star, then we define y to be the integral of f. So this is how we define it. And we're going to show two things basically. First of all, we're going to, at least we'll admit them because again, proof is quite tedious. We're going to admit like the existence of it, and uniqueness doesn't, again, because the x star separate points, you can't have uniqueness problems. Because if this is true for every lambda of x star, and there's another y here, where lambda y equal lambda y1 for all y, then they're going to be equal because x star separate points. So there's no way they're going to be different. So we don't have the uniqueness of the integral problem here. Now we're going to admit this following theorem about the existence. In the special case where Q is compact, F is continuous, and the convex hull of compact sets, F of Q is going to be compact, which is true in Fourier spaces automatically, right? So suppose X is a topological vector space on which X are separate points. Mu is a Borel probability measure. A Borel measure, if you remember, is from measure theory, where it's just a measure on the set, on the sigma algebra defined by the open sets, created by the open sets, and a probability measure just has the mass of 1. So the measure of the entire space is going to be equal to 1. On a compact Hausdorff space Q, if f is a function from Q to X, it's continuous, and if the closed convex hull of f of Q is compact in X, which is true in Fourier spaces in this case, then the integral y equal integral of f is going to exist in the sense that we defined it earlier, which means that lambda of y equal integral lambda of f. And finally, y is going to belong to the closed convex hull of f of q. Now, a remark, you would be asking me, okay, we've proved this for probability measures. What if I want my measure to be, not a probability measure? And this is the fact that we can resolve easily. Because if v is any positive Borel measure on q, then some scalar multiple of mu is going to be a probability measure. So the theorem holds except for its last sentence, this one, with instead of mu, which means that we can extend it to real value Borel measure by the Jordan decomposition theorem. And if the scalar field is C, we can extend it to complex one. Now, this is a nice theorem. We're going to show that every y in the closed convex hull of a complex subset R of X can be presented as the weight average of R, which is the more interesting part of this section. So if X is the topological vector space where X stars separate points, and R is a compact subset of X, then the closed convex hull of R is going to be compact, and the closed convex hull of R is compact. Then every Y in R is going to be. Wait, just give me a sec. I think this is supposed to be Y in H4. It's mistaken. A sec. Unless I'm going crazy. I remember it being in. Just to be sure I'm not missing the condition. Yeah, I know. If it's in the closed convex hull, so I made a mistake here. This is not R, this is H bar here. So Y is going to be in H bar, the closed convex hull of R, if and only if there's a regular probability measure mu on R such that Y is equal to integral of X d mu. So it's basically as here, the weight average of R. So small detail I'll fix after the meeting. Now, in order to prove it, let's see. This is a nice proof because I think it utilizes a lot of previous things we learned, like in measure theory, and it utilizes the weak topology and things like the alagalo. I don't know how you pronounce it, but bear with me. So if X is a real vector space and CR is the Banach space of all linear continuous functions of R with the continuous norm and the Rice representation theorem, you can find this in RCA chapter 6 if you want, and chapter 2 for a simpler version. It identifies the dual space CR with the space of all real polar measures on R that are differences of regular positive one. So now that we have this identification, I can define phi from a dual of CR to X. So it turns every mu to integral of x d mu of x over R, right? And if P is the set of all regular polar measures on R, then the theorem just tells us that the image of P is the closed convex hull, right? Because we want the image to be these, because every y here is out to be this, so we just have to prove this value, right? So every x belongs to R is, we take the unit max, or this is, I think is called the Dirac delta function, which I think is important in distribution theory specifically. So we take the unit mass contrasted at x, it belongs to P, right? Because the image of it is going to be x itself. And this shows us that R is subset of phi of P. And because phi is linear and P is convex, and the linear image of convex sets is convex, this means that phi of P is a convex set that contains R. So specifically, it's going to be that H is subset of phi of P, right? Where H is the convex hull of R. Now, by our previous theorem, we know that phi of P is a subset of R. So all we need to show is that phi of P is closed, right? Because if it's closed, then we are done. Just take closure here and done. And this is a concept because of the following two facts. First, P is weak star compact in the dual of CR, and the mapping phi is continuous if CR star is given its weak star topology and if X is given its weak topology. I'm going to only prove one. I'll leave to you to check into it just for sake of time. So once we have these two results, it follows that phi of P is going to be weakly compact because it's going to be the continuous image of a compact set, right? And because it's weakly compact, it's going to be weakly closed. And because weakly closed sets are, remember, this is due to the Hausdorffness of the topological vector spaces, which is always nice. And because this is the key fact, because weakly closed sets are strongly closed, then we get our desired conclusion. So, to prove one, notice that P, remember, P is the set, where to define it, is the set of all regular polar probability measures on R. P is going to be subset of mu such that the integral h is less than 1, so the norm of h is less than 1. And this norm makes sense over C of R, where we define it here, CR. So, and this large set is going to be weak star compact by the Banach-Alaoglu theorem, right? We have, this is just a special case of it. So it's enough to show that P is weak star closed in this case, because if it's weak star compact, yeah, if it's weak star closed, then it's going to be weak star compact itself, because closed sets of compact sets are compact. Now, if H belongs to C of R and H is positive, then we can set EH to be mu such that integral of H is positive. Now, because the map that takes mu to integral H d mu is going to be continuous, then by the definition of the weak star topology, every EH here is going to be weak star closed. And so is this set, E. Now, because P is the intersection of all these sets alongside E, P is going to be weak star closed. And we got our proof because we want it to be weak star compact. And yeah, that would be the proof of this theorem. We have showed that in this situation, every element in the closed convex hull can be represented as the weight average of R, which is what we have proved here in this theorem. Let's see. So we leave the proof of 2 now, for now. And finally, for vector value integration, we have this inequality, which is a slightly stronger conclusion than what we have proved earlier. Remember, all integrals that are present here are going to be understood how we define. So if Q is a compact Halter space and X is a Banach space, then f from Q to X is and f of Q to X is continuous, and mu is a positive Borel measure on Q, then the norm of the integral is just the integral of the norm, which is what we, expect to be. Now, if we set y to be the integral of f, then by the Banach theorem, we can find a lambda and x star such that lambda of y is equal to norm of y, which I think is also proven in Rudin. Now, and lambda of x is going to be less than norm of x for every x in x. In particular, lambda f of s is going to be less than norm f of s, all s in Q. Now, by the existence here of the integral itself, we know that the norm of y, which is lambda of y, which is the integral of lambda of y, because that's how we defined it, and it's going to be less than integral the norm of f due to this fact. So this shows this inequality. Okay, and the last section, I didn't include the, don't worry, I didn't include the massive proof, which I think you have to check it out, but for holomorphic functions, it essentially comes down to a crucial fact. First of all, we do want to generalize the concept of holomorphic functions, which is going to be useful in our study later of Banach algebras. So it's useful to have the concept of holomorphic functions that are vector valued, right? There's even, you can even like generalize the domain itself to include just more than your normal values from your space, but that would be for a very wide topic. Basically, any result we have proven in differential calculus on Banach spaces, you can try to generalize this to even topological vector spaces. So you can have, here we'll only show like the weak holomorphic values and strong holomorphic values. You can even go as far as to start showing like things related to the Fréchet derivative. So we turn to study of holomorphic functions that are vector valued, which can be useful in the study of Banach algebras in some other contexts too. Not sure if anyone has any ideas where these are present. I'd be welcome to it, because I've only seen it in this setting. Now, there's two natural ways to define holomorphic functions right now, which is of course like the weak one and the strong one. The weak one is, as you would expect it, a function is going to be weakly holomorphic if lambda of f is holomorphic in the usual sense for every lambda in x star, right? Now, the surprising fact we're going to prove, and the strong holomorphic one, of course, is like your usual holomorphic definition, and which is the limit of the scalar with this vector. This exists for every z in omega, where omega is an open set, so the differentiability makes sense here. Now, what's surprising and what we won't prove, but you should check out the proof for it, is that in a Fréchet space, these happen to be the same concept. We already know that the strongness would trivially imply the weakly one, right? Because lambda is continuous. So if this exists, then obviously the lambda of s is going to be holomorphic. But the opposite direction is the one that's non-trivial. So recall, if gamma is a closed path that does not pass through C, then the index gamma of z is going to be 1 over 2 pi I. Sorry, there's an I here. I'm pretty sure I forgot it everywhere, actually. Yeah, I did. There's supposed to be, so every time you see 1 over 2 pi, it's 2 pi I. Forgot it for some reason. Integral of gamma df d zeta of zeta minus z. And all paths here are later going to be piecewise continuously differentiable, or at least rectifiable. Now, the continuity of lambda, as I mentioned, it makes it obvious that every strongly holomorphic function is going to be weakly holomorphic. The converse is true when active if you share, but it's not obvious. So I think there's actually other methods to prove it, but this is the one that Rudin follows at least. So if omega is open and X is a complex Fréchet space, then F is weakly holomorphic, then the following conclusion follows. So here's what our strategy is going to be. I won't go into the proof, but I'll tell you like in general what's going to happen. First of all, we're going to prove that F is going to be strongly continuous. The key fact that we're going to use here, there's a certain theorem that relates weak boundedness to strong boundedness, which we're going to use. And after we prove that F is strongly continuous in omega, we turn to prove that the Cauchy theorem and Cauchy formula hold if gamma is which are that is gamma is a closed path in omega such that the index of W is 0 for every W not in omega. I think it has a name, homologous to 0 or something. I don't recall like the specific name. This concept has a name. Then the integral gamma of f d zeta is going to be equal to 0, and f of z going to 1 over 2 pi I here. Integral gamma of zeta minus z inverse f of zeta d zeta if z belongs to omega, and the index is equal to 1. And if gamma 1 gamma 2 are closed paths in omega, then the indexes are equal for every omega. every w not in omega, then the integrals are going to be equal. This is similar to something you may have seen in residue calculus, or residue of complex analysis somewhere. And using the Cauchy theorem and some pretty tedious details, you can show using the Cauchy formula that F is strongly holomorphic in omega, which means that in Fouché spaces, weakly holomorphic and strongly holomorphic are the same concept, which is always nice because the weak topology is in general nicer to work with, is the value. And finally, another theorem that's going to help us later in the study of spectra of Banach algebras is a certain extension of Liouville's theorem, which, if you remember, is that bounded the entire functions are constant. Now, holomorphic, of course. Now, if X is a complex topological vector space on which X stars separate points, and if S is a function from C into X is weakly holomorphic, and f of C is weakly bounded subset of X, then F is constant. So our proof is similar to what we did earlier, where did we do it? There was a situation here where we moved to a setting that we know how to work with. I'll have to check anyway. That's just not to waste time. So for every lambda in X star, lambda f is a bounded complex value entire function. If Z is in C, I don't know why this is here. It follows from Liouville's theorem. So we are back now in our usual setting. Oh, I remember now. Okay, let me finish this first. It follows from Liouville's theorem that lambda f of z is equal to lambda f of 0. And again, because X stars separate points, which is something that we have used multiple times now, then f of z is going to be f of 0 for every z in C. Okay, I remember the situation. We used it. Just a sec. Because I know that this is a common theme, so I want to highlight it. But just a sec. Here. So we had a space. So in order to prove it, we moved to a locally convex space where we can apply a theorem we know. So this strategy is what we used in the proof of Liouville's theorem. We moved to a space that we know how to work with, and we proved it. So this strategy of trying to move to a location where you know how to work with, and then use things you know to determine results about the other space have been showing up quite a bit in these two places, at least. So this is what we done here, which I think is obvious that you think about it, but it is a good strategy to keep in mind. And yeah, that would be it for now about the presentation. Hope everyone thought it was clear again.
Yeah, very clear, very good.
Yeah, it was very nice.
Sounds good. Okay, so for this week, let's see. Also, I guess I want to say one. In case you haven't solved exercises, I would highly recommend these two exercises. These two actually have a name. I forgot which name what the name of the theorem was, but these are essentially because in certain spaces that are not metrizable, we can't really relate compactness with sequences as we normally would, because sequences don't describe the space in metric spaces entirely. But in the weak topology, at least, you can actually get a result of converged subsequences rather than subnets, which is the general setting, which surprisingly can't happen for weak star topology. So this is something that I want to mention. This has a name. I think he mentions it here somewhere, but I thought it's pretty interesting because it basically gives you a tool where if you are working with if we share space, then you can still get the concept of here called I'll send it in chat, the Eberlein-Smulian theorem. I think it's pretty good because it relates basically conversions to nets, to sequences, essentially. It relates compactness to sequences. And yeah, that would be it. I'd say for next week, Bangu, would you be able to do the next week presentation?
Yes.
Right. Which actually might, this is something I want to discuss. So next week will be our last basically theoretic week, which is chapter 4. And once we start Banach algebra, do you guys want to continue with the presentation style, or do you want to have like, since it's like basically just applications, we can have a more just discussion type of meeting if you guys want. Would you prefer this over presentations? Starting from this chapter, basically. Let's see.
I haven't read enough in chapter 10 yet to know what makes the most sense, but it seems like a reasonable idea.
Because it is like, all right. So I guess Bango will be handling the final presentation next week, which is duality.
It looks like chapter 4 is short enough that we can do the whole thing in 1 week. Yeah.
Yeah, that was what
Okay,
has
cool.
planned.
Yep, we'll do
All right.
it.
So Monday, same time?
Yeah, fine for me.